Now I want to take some time to talk about linear approximations as well as differentials. Talk about them at the same time because the two subjects go very close together. All right, so first of all, as far as linear approximation is concerned, what's it used for? Okay, what would be the purpose? Well, let's say we had a function. Draw my x and y axis here. And we had a function that maybe part of it looked something like that. Well, let's say for the sake of argument that this function is the type of which is perhaps a little bit difficult to evaluate for certain x values. In other words, you can't always just plug in an x value and easily mentally evaluate this function. Now, let's pick a number. We'll call it a. And ideally, this number is a value for which it is easy to evaluate this function. So this point would correspond to f of a, and again, we're going to assume for the sake of argument that that is a easily evaluatable value. So I'm going to come in here and I'm going to draw the tangent line, the line that touches that function at a. Now, if you were, and by hand I can't illustrate this very well, but if you were to stay close to a as far as x values are concerned, if you were to zoom in on that region, what you would discover is that the line, and from now, just for this moment, I'm going to call that y equal mx plus b, that line would do a decent, a fairly good job of approximating the function values. And the thing about using the line is linear equations are always easy to evaluate, where this f of x may not be easy to evaluate. So our strategy is going to be to approximate function values by using the tangent line. You will have to stay very close to that a value. If you venture out very far, as you can see just in my illustration, function values and the linear equation values do start to have a gap between them. They do diverge from one another. But as long as you stay close to the a, that's not going to be a problem. You will be easy. It will be easy to evaluate values around the a, again, because linear equations are easy to work with. Now let's go back and talk about linear equations just for a second and think about where this is going to come from, how this line is going to be developed. Remember, the point slope formula for a linear equation is y minus y1 equals m times x minus x1. Well, we're assuming that we're using the point a, f of a in this scenario. So this equation immediately becomes y minus f of a equaling m times x minus a, again, assuming that that's an easy to obtain value and easy to evaluate point. Furthermore, the slope is found using derivatives. So this becomes y minus f of a equaling, instead of m, we'll call that f prime of a. And in one last step we saw for y, and this line isn't just any line, it is a linearization of the function. So switching notation, our linearization for x values close to a will be equal to this f of a plus f prime of a times x minus a. Now, where would this be used? One thing that pops into my head immediately is with square root functions. Square roots can be difficult to evaluate. So if I wanted to know what is the square root of a 100.7, that is not an easy value to evaluate, but it's very close to 100. All right, it's very convenient that the fact that it's close to 100 makes this very convenient. So I would let my a equal 100. I would let my function be the square root function. So I'm going to need the derivative. Derivative of square root of x is 1/2 times x to the negative 1/2 power. F of 100 is 10. That's easy to evaluate. F prime of 100, lucky for us, is not a problem either, because this can be written as 1/2 square root of x. So f prime of 100 is 1/2 square roots of 100, which is a 1/20th. Right, so therefore the linearization of that function is the f of a, which is 10, plus f prime at a, which is 1/20th, times x minus a being the 100th. So that is a line that touches the square root curve at the point 100, 10. And I'm going to use it to approximate the value at 100.7. So the linearization gives me at 100.7 a 10 plus 1/20th times 100.7 minus 100. That's a 10 plus 1/20th times a 0.7. And that's some pretty easy arithmetic. And yes, I'm going to cheat a little bit. I don't feel like doing the arithmetic. So I'll take the 0.7, divide it by 20, add it to 10, and I get a 10.035. If you compare that to a calculator evaluated, you notice that at the third decimal place, if you round to the third decimal place, I was dead on. All right. So again, the concept behind linearization is pick an easy number and evaluate near that number and use that linear equation to approximate near certain values. There are linearizations that are actually pretty well known and commonly used in different communities. For example, in the physics community, math as well, but physics and engineering more so, it is convenient sometimes to try and come up with a linearization for things like trig functions, like sine of x. All right, so let's let sine of x be our function. That means our derivative, cosine of x, and a convenient place to evaluate sine would be at 0. Why? Because the sine of 0 and the cosine of 0, for that matter, are easy. So for angles close to 0, let's see what sine of x becomes. F of 0 is 0. F prime of 0 would be 1. So sine of x can be approximated by, and again, our formula is going to be f of 0, which is 0, plus the slope, which is 1, times x minus 0, and this simplifies down, I got my x there, to x. So what we find is the sine of x is approximately x when you're close to 0. And that can be tested on the calculator. One thing you have to be sure of is that you are in radians. Everything we do in calculus, especially as it pertains to trig functions, is dependent upon our use of radians. So if I want to take the sine of 0.001, I would expect that that would be close to 0.001. And if you round that to 3 decimal places, that's what you get, 0.001. Now this isn't going to work forever. If you take the sine of 0.1, that's still pretty close, I will admit. But the sine of 1, I believe by that point, is starting to get a little bit further away. Sine of 2 is getting much further away. So again, you have to remember, these approximations can only be used when you're close to the point around which you built the line. You know, a differential is actually something very close to a linearization, which is actually a simplification of. Remember that f prime of x can be represented, symbolized, whatever, dy over dx. When you first see that notation, that dy dx notation, you're often told, hey, that's not a fraction with a numerator and denominator. It's a symbol. It's not like it can be broken up and treated like a fraction. In reality, you kind of can. I can multiply both sides by dx, and I find that dy is equal to f prime of x times dx. But in this application, in this scenario, we need to understand what is dy, what is dx, what do they mean by, f prime of x, what's the difference between a dy and a delta y, what's the difference between a dx and a delta x, right? So, again, the drawing, if I had a function that looked like so, and I came in here, picked a point, and drew the tangent line to the curve at that point, and then looked some distance away. Here is an x value, and if I move some distance, delta x, in other words, if the distance from here to here is delta x, I would arrive here at x plus delta x. All right. Now here I have a y value for x, and over here I would have 2 different y values. All right. One of them is the y value for the function. The other one is the y value for the linearization. All right. So notation. Delta x is the actual exact, not an approximation, but an exact change in the x value. Notice that delta x and dx are going to be the same because this change is, well, controllable. So the amount that I choose to change the x and the amount that x actually changes, they're the same. All right? But here is what's different. If you draw in an imaginary horizontal line here, this distance right here is the exact, precise, the perfect measurement of how much y really changed, known as delta y. In this particular approximation, this larger number out here is how much you would have, how much the line would have predicted for the change in y. So the dy dx is the slope of the line. The dy is the change the line made. The dx is the same as delta x. That's the change of the x. And f prime of here again, is the slope of the line. So in other words, what's being said here is that the predicted change in y is equal to the slope of the line times the change in the x. Let's look at an example that brings all of those factors together. Right? Let's say you have a sphere. All right? You have like a balloon. And the radius of that sphere is measured to be 21 centimeters with an error at most of 0.05 centimeters, and wants to know how much could you be wrong? What kind of error might you make about the volume of that sphere using this measurement that you know could be off by a little bit? Well, we know that the volume of a sphere is equal to 4/3 pi r cubed. Therefore, dV/dr would be equal to a 4/3 pi, bring down the 3, drop the r to the second power. Clean it up a little bit. 3's cancel, and it's a 4 pi r squared. That's your dV/dr. That means the deviation in volume is equal to a 4 times a pi times a radius squared times any deviations or errors in radius. Therefore, deviation in volume, as explained by this error, is equal to 4 times pi times radius, which is 21 squared, times deviations in radius. Right, on the calculator, 4 times pi times 21 squared times a 0.05 tells us that the volume could deviate by as much as, if you want to cut it off at a whole number, 277 cubic centimeters as a result of that possible deviation or that error in radius. All right, and that is how a differential is used. And you can see this same type of calculation could be done with a linearization. All right, anything you can do with the differential, you can do with a linearization. But the differential is quicker and shorter. You don't have to find the entire equation of the line, and all you're trying to do is look at possible errors.